Hello, everyone. Thank you for coming to this session. This is Diogo Monica. He tweets at Diogo Monica. He is security lead for Docker. As a security lead, you can do kind of whatever you want. So one of the things he did today is actually change the title of this session. So it was probably listed as using Docker to secure your traditional app, but really it's going to be about going fast while protecting your data.
Perfect. Thank you for the intro. I don't do everything I want, so that's actually not true. But today I want to talk about the Docker 500 and how you have to go fast while protecting your data. Hopefully this talk will give you a little bit of insight on how the security team at Docker thinks about security. And obviously I added a lock emoji, so everybody's on the same page when it comes to the fact that this is a security talk. Good. Before I go into the talk itself, let me tell you a realization that I've had over the past 10 years of working in security. It turns out that security engineers, they operate largely shielded from the impact of data breaches and the outcome of people being compromised. I used to work for a company called Square that processed credit cards for small merchants. And I understood intrinsically what it meant for a credit card to be stolen. Personally, I knew what it meant, what was the pain of a credit card being stolen, and the process that I needed to go through to recover from this. What took me a lot longer to realize was the impact of one of the merchants to be compromised, have a chargeback, to have money be stolen out of their bank account. It was only much later that I realized that this actually meant that they would go to loan sharks, or sometimes simply close down their businesses. And so this led me to look back at my career over the past 10 years and take a different look at it and try to understand really what security means and what we as security engineers should be doing. And so today I want to walk through an example that I think is a perfect example that exemplifies the impact of data breaches and the impact of our jobs as security engineers. This is a study by the Vanderbilt University on hospital data breaches. Very obviously represented by an attacker stealing all of the data from a hospital using their iPhone. They studied the impact of data breaches on hospitals on the 30-day mortality rate. So what they concluded was, in the first hand, that the hospitals, as they digitized patient records, were actually getting better at saving people's lives. The 30-day mortality rate kept coming down. Mortality rate on the y-axis and the time on the x-axis. So as time went on, mortality rate is coming down for the past 10 years in US hospitals from 2011 to 2015. So this is great. There's been a causal effect between digitation of data and 30-day mortality rate coming down. Awesome. But as they say, more data, more problems. And having more data means that you're also necessarily going to have more data breaches. And so the study went to see what was the impact on the hospitals of these breaches. And hospitals are not normal companies. When a data breach happens at a hospital, people die. And so they concluded that data breaches were associated with a higher 30-day mortality rate following the couple of years following the breach. They actually concluded that this was the same as undoing a whole year of improvement of digitizing patient data. So this is absolutely awful. You can see in this graph that the mortality rate in red of a hospital that never gets breached continues going down, but the mortality rate of hospitals in blue that get breached has a spike around 2 years, 1 to 2 years after a breach that signifies that the mortality rate is regressing and that people are dying unnecessarily. So at this point, I hope we're all outraged the same way that I'm outraged. And I hope at this point that we're all calling for more security in hospitals to ensure that data breaches don't happen again. So show of hands, who's for more security in hospitals to ensure that we don't have data breaches? Show of hands. Perfect. Everybody. That's great. Except that we're all wrong. It turns out that security was the problem. The reason why people were dying was because the hospitals were overcorrecting on security. And by overcorrecting on security, they were making their processes less usable, and people started dying because of it. It actually got worse. By making security harder, the nurses and doctors started going outside of the security processes, making the data even more exposed, causing more data breaches, and effectively creating a cycle. So, patient outcomes at hospitals are getting worse because we overcorrect on security measures. We're introducing usability changes that affect and frustrate the clinicians and disrupt the patient healthcare. I've always thought that these problems could just be solved by adding security and making the security process better. But it turns out that we are the ones killing people, not the attackers that are breaching these hospitals. And so I realized that the same way that we have been failing the clinicians and the hospital doctors, we've also been failing developers and ops and really everyone that has to use a system that deals with data that is sensitive to affect anyone else. And I believe that the main problem, one of the main reasons why this is happening, is really the word that we use to describe our discipline: security. Security means the state of being free from danger or threat. But really, if there's one thing that we know to be true, is that if you connect the system to the internet, you are constantly threatened and you are constantly in danger. So instead of talking about security, we should be talking about safety. And we should be protecting our data and our patients from danger, risk, or injury. It is not just about security. It's really about good security allowing you to move fast as possible while being safe. So this realization led me to think about how can we do fast security in a safe manner. And you know what I think about when I think of going fast? I think about the Indy 500. This is me and my colleague Nathan McCauley using our favorite hats in the whole world. And we're at the first Indy 500. First time I've been to Indiana. Since we're in Europe, I replaced the Indy 500 with Formula One so I can connect better with the audience. And so replace the hat and replace the logo. But it's effectively the same thing. There are a lot of things that are curious about the Indy 500 and about Formula One. And one of them that is particularly relevant for this is the fact that these cars are moving incredibly fast. Yet, people are constantly excited about the crashes themselves. And for me, that didn't make any sense. It's very clear that at this speed, if somebody crashes, the pilot cannot survive. Let me show you an Indy 500 accident. It's a pretty bad crash. So this can only be described as an utterly and complete failure of the underlying infrastructure that is supporting this driver. The infrastructure, completely failed. However, Scott Dixon, the driver in this video, walked away from the car on his own. The security of our data, I realized at that moment, should be designed to be safe, no matter how secure or what happens to the underlying infrastructure. So we, as security engineers and operations people, should be architecting our systems to protect the most important thing we have, our data, the same way that the engineers from the Indy 500 and Formula One designed their cars to protect their most important cargo, the humans. So I was really curious about these cars and about how they were protecting the passengers. So I went to look for the security features of the Formula One and the Indy 500 and what they were actually doing. Clearly they know what they're doing if they can have somebody walk away from that kind of catastrophic failure of the underlying infrastructure. And it turns out that immediately there were two things that they split. Number one, they thought about this as pre-crash So measures that have to be implemented and ensured as safe before a crash, and measures that they did after and during a crash. So let's look at some of them. That animation was 20 minutes of my life, so I really hope you appreciate it. There's 4 things that I think are mainly the most important ones before a crash happens. These 4. And during the crash, they also have a set of 5 different things that I think are particularly important and that are protecting the drivers. And so I realized if they're doing such a good job at protecting humans, surely they must also be amazing at protecting their own data, right? Well, turns out they're not. So even the folks that are so good at protecting these cars and these humans and these drivers are not great at data security. So really, it's up to us to look at how they protected the cars and try to map it out to our world to protect our own infrastructure. And that infrastructure is represented by the server, which is going to speed away in that direction so that we can actually look at it one by one. So let's take the same pre-crash 4 items that they did and that I demonstrated for the Indy 500, and let's see if we can apply it to our infrastructures, if there is a mapping, if they make sense. Let's start with the first one. The first one, pre-crash on Indy 500, is stringent, dynamic, static, and load tests to ensure the safety of the drivers. The way they do this is they ensure that their cars have a process that they go through tests before they ever go onto the racetrack that are more stringent and more adversarial than any kind of race day conditions they can have. What that means, for example, is they test the cars in all possible conditions such that on race day, the cars always operate within the guidelines that they've been tested on. What does that mean for us? Is that an equivalent? Well, there clearly is. If we have a trusted, repeatable, and adversarial CI/CD pipeline, what we have is effectively a repeatable way of testing any change to our applications. Not just a point in time, but any change of our applications goes through a stringent process to understand if they can support the actual conditions that they're finally going to be exposed to in production. Good examples of this are if you have less load in staging than you have in production, you're testing in production. If you don't have adversarial scans for remote code execution and SQL injection in your staging environment, you're testing in production. If you are not consistently scanning and understanding the kinds of vulnerabilities that your applications might have before sending them to production, you're testing in production. And if you don't have a repeatable process that is signed and that is trusted at every single step of the way to get there, then you don't have trust of the final outcome. So this is a really important thing that we can do that matches their number 1 pre-crash item. Let's go to number 2. They have a cockpit that is surrounded by a deformable crash protection structure. So they design for the worst case. They have the car built around this structure whose sole purpose in existence is to protect the driver. And they test this all the time. What is the equivalent for our infrastructures? Well, it turns out that we don't think about things this way. We're not designing our applications and our infrastructures to think about the data immediately. For example, if we are designing an application, and for example, imagine that this is an application or a container or servers, and we're on the board with a customer or with our internal networking team, and we have these applications, and we start drawing these kinds of lines between the applications, which effectively represent the communication flows. When you design and when you draw a line between 2 applications, what a developer sees is secure communication, independently of what it actually is. So even though you draw something like this, a line, what they see is a line with locks. So their assumption is that this is safe, that this is secure, that this communication path of their applications is already taken care of. And as we know, that is not true. So really, it's our job to think about this, to think about the expectation, and to ensure that by default, they have the ability of guaranteeing that that infrastructure is safe, and that every single piece of communication that goes through these lines meets their expectation, and it is secure. And the way that you can do that is obviously by having something like mutual TLS between every single one of your applications or every single one of your servers or your containers, and ensuring that you have authenticity, integrity, and encryption of all of your data. But not only that, we talked about a deformable crash structure. You should allow people to design their applications from the get-go in a way that allows them to segment access to portions of the infrastructure based on their level of criticality. This means that sensitive systems are never exposed to the internet. So if an attacker compromises an internet-facing system, this structure deforms, and they will not have access to the final data. They will only have access to the intermediate servers that are not as sensitive as the data itself. So this is our equivalent to a crash-protected structure. You can compromise the outer layers without impacting our driver, in this case, our data. Okay, number 3, pre-crash check items. Before the race, all drivers have to demonstrate they can get out of the car within 5 seconds. This is effectively not designing for the worst case, but actually testing the worst case. What happens when you crash? You're going to have to get out of the car, so show me that you can get out of the car under 5 seconds. And if you can't race today. So the equivalent for us is dealing with the worst case scenario in testing and practicing their worst case scenario. And one of the things that happens all the time to us is this. Cowboy developer goes and makes the deploy a lot more convenient by adding the private key into the repository and pushing it to a public GitHub repo. This is more convenient for everyone. So now the problem is you have a private key accessible to the internet. And this actually happened, for example, with Adobe, with the GPG key a couple of weeks back. So now the question for you, can you or can you not get rid of the trust in this key under 5 seconds? Can you get out of this car? And so you should design your systems and you should train to actually be able to deal with this. So one of the things that we focused a lot at Docker was every time we designed a system that used keys, such as Docker Content Trust that allows you to do signing of your images, we designed a transparent key update process. What that means is that if Cowboy developer does commit a private key into GitHub, you will have a transparent way of rotating the trust throughout all of the consumers of this key under a maximum reasonable amount of time, minutes, if not seconds. So this is how you should think about your infrastructure. And this is what you should practice and demonstrate that you can do before you go to the races, before you deploy to production. But it's more than this. It's not just about signing keys and keys that operate on top of your infrastructure. You should really care about the underlying infrastructure itself. So let me give you an example. Imagine that you have a 4-node cluster. You have a manager, which is the most important node in the system. This manager has a certificate authority, which means that this manager has private key material that is necessary to issue identities and TLS certificates for every node joining the system. So 3 workers, unprivileged nodes, 1 manager, privileged node. What happens if a manager or if a worker gets compromised? Well, you remove the worker. That key no longer has any trust in the system or can no longer be used, and then you effectively rejoin the worker, and now you solve your problem. That's pretty easy. But what happens if a manager gets compromised? What happens if the attacker has access to the actual key material of the certificate authority there? In a normal system, in a normal security engineer will effectively answer that question with a shrug. You should redeploy your cluster. You should scorch the earth and start from 0. But the reality is that this is not practical. And the compromises of keys not only happen when somebody goes and attacks your infrastructure. By and large, the way that these compromises of keys happen is backups of keys, leaks of keys in logs, such as PagerDuty, so on and so forth. So the realization is that you have to have transparent key rotation in every single portion, in every single layer of your infrastructure, including your core components of your infrastructure that are actually managing the nodes. And so that's something that we actually did. The way that we did it was if you have trust in a certificate authority that is blue, for every single node in the system, we allow you to generate a new certificate authority, which is red. We do a cross-signed certificate from old certificate authority to new certificate authority. We force all of the nodes to have new certificates be reissued that trust the new CA and have a path to the old CA. And then the final step, we force a new rotation of all the nodes, ensuring that they no longer trust red, they only trust blue. So this is the kind of mechanism that you have to make sure that you can use to get out of your infrastructure or your car in under 5 seconds. And the final one for the pre-crash safety features is constant monitoring and replacement of tires. Let me show you what actually happens when the best pit crew in the world does the fastest rotation of tires ever. I want you to watch that again. That is 1 second and 92 milliseconds, slightly under 2 seconds, for them to not only add gas to the car, but rotate every single tire. And I would like you to notice that they're not trying to fix the tires. They're just replacing these tires. And I also want you to notice that they are proud of the fact that it takes 1 second and 92 milliseconds to change the tires. They're not proud for taking 2 minutes, 3 hours, and see who takes the longest. So why in hell do we, ops, why are we proud of the fact that our servers have been alive for 3 years? Why? Why are we not exactly like the pit crews, constantly replacing our servers and effectively bragging to each other about the fact that the server that has been alive the longest has been for 2 minutes? That is something to be proud about. 2 years, don't care. 2 minutes, that is amazing. I want to hear about it. And so instead of tracking uptime, the time that a server has been alive, you instead track reverse uptime. And one thing that happens when you track reverse uptime is that you align the metrics that the security people use with the metrics that the operations people use. It is very interesting for an operations person to have a maximum time that a server has to live. Why? Because if you constantly replace these servers, they can't drift. There is no server drift. And it turns out that server drift is one of the biggest causes of downtimes for operation people. It also turns out that for the security folks, you can't backdoor a system that is constantly being reimaged. So from a security perspective, that metric also helps me track the security of my system. So this is perfect alignment between security teams and operations teams in terms of not only security, but stability of your distributed system. And the other thing that you have to track, and that also aligns security people with ops people, is tracking the golden image freshness. This means that when was the last time that you updated your golden image, that you patched the vulnerabilities present in this golden image? Because if I'm a security engineer, and I patch a golden image, and my team is tracking reverse uptime, then I know that there's a maximum amount of time that it will take for this patch to go out to my infrastructure. Which means that kernel updates that are coming out with Linux, O-days all the time are now easy to handle. You have a system that rotates all the servers. You're tracking the maximum amount of time a server has been alive, and you're constantly patching your golden image. This is what I mean by alignment. This is something that we should be proud of. Okay, so now what if our server impacts, crashes, and burns? What happens then? Well, let's go through the 5 main things that the Indy 500 team does for their cars. Number 1, the driver, when there's a crash, doesn't simply get removed from the car. They have the ability of taking out the whole seat. Not take out the driver, take out the whole seat. Seems a lot easier to me. What that looks like is if there's a crash, you don't need to, like a normal car that you drive, like a Prius, and saw open the car, take 2 hours to extract the passenger, while the passenger, in this case the driver, could be in distress and could be dying actively in front of you, and it's going to take you 2 hours to bring in the firemen and to saw open the car in a secure way. You just lift the seat and get it done with. What is the equivalent for our infrastructure? Well, if you're using Docker containers, you get to do something really cool. You get to freeze the container. Not only the file system state, but really also the memory state. If a container is misbehaving, instead of going in, trying to analyze what is going on, trying to fix it, so going with your saw and trying to open the container, what about you freeze the memory, freeze the state, move it to a network that is no longer critical, restart the container, and then go inspect it later. This is the equivalent of lifting and shifting the seat. You freeze the current misbehaving container, and then later you get to it, and later you go inspect it after you solved your production problem. The second component is a HAN system, which means head neck, and shoulders. And it absorbs and it distributes the force of an impact. So effectively, it saves the skull and the neck muscles from having the brunt of the impact because it distributes it throughout the rest of the body. So the Hans system looks something like this. And what is the equivalent for our infrastructures? Well, if you want to redistribute the force of a denial of service, or the force of a peak load when you get slashdotted or hacker newsed and everybody's just hitting your site, what you should have is the ability of not only having auto-scaling, but having automatically load balancing throughout all of your applications. And this, again, is what the expectation of the developers is. They don't care about the number of instances. It should be automatic that the number of instances match the number of requests. And it doesn't matter if you're a security person or you're an ops person, you're a developer person. And it doesn't matter if it's a denial of service or if it is just a peak in usage. The solution is the same. It should be available. It should be automated for you. Okay, number 3. Fire-resistant suits that withstand fire for 11 plus seconds without warming the suit above 41 degrees. For the Americans in the audience, that is 104 Fahrenheit. Since it's in Europe, obviously I use Celsius. And this, by the way, is not what the suit of a driver actually looks like, but I thought the picture was funny. So when the driver is on fire, the suit makes sure that the temperature of the body doesn't go above 41 centigrades. That is pretty cool. How do we do that for our infrastructures? Well, we sandbox them. And by putting an application in Docker, you're effectively adding a sandbox to your application. You're only making it more secure. The reason why the sandboxing is like the fire-resistant suit is because the sandbox, in this case Docker, has all of these different mechanisms. SecOm policies, SE Linux, AppArmor. It comes with default capabilities dropped. It comes with all of these secured by default capabilities and systems to enable, if an application gets compromised, the attacker is contained and is trying to escape, and you're trying to contain the fire for as long as you can. Attacker is in, but can't do damage to your infrastructure. You currently are on fire, being actively exploited, yet it is not impacting the rest of your infrastructure. So it gives you time to respond, gives you time to get to the driver. Another way that you can think about this is how can you make the data that you use inside of your data center useless outside of your data center? This is a shameless self-plug of an article that me and Nathan McCauley got on Wired this week, so I had to put it up. And the way that this works is we made up this term that we thought was really cool and that we wanted to try to push out to the world called crypto anchoring. Crypto anchoring means a way to hold your data such that it cannot be operated outside of your data center, neatly represented by an anchor that also is partly a key. The way that this works is that the data that you have on your databases can only be operated on or decrypted, for example, a social security number, if you're within your data center. By using a hardware security module and having a key inside of that hardware security module, a hardware security module that is physically attached, bolted to your data center. This means that a data breach that leaks all of your data outside of your data center is no longer useful for an attacker, because the attacker needs persistent connection to your infrastructure. It needs to be within your infrastructure asking for decryptions from your crypto anchor for it to actually have any useful data in return. And this gives you the possibility of detecting attacks instead of just having one chance of detecting it on the initial attack and initial exfiltration. The attacker effectively becomes a bull in a china shop, just walking around and crashing all the vases everywhere. In this case, in our analogy, the vases and the crashing would be your intrusion detection system. Number 4 is not the resistance of the suit itself. It is a fire suppression system that you need to have available that can be activated not only by the driver, but also by the race marshals. The reason why this is interesting is because imagine that the driver crashes and the car is on fire, but the driver is out. It's effectively passed out. It cannot activate its own fire suppression system. This is when it's useful for a fire marshal to be able to do it remotely. So this is an example where the car is, there's no driver in there, don't worry, the car is completely gone, but I thought it was a funny image. But for us, what that means is that if your infrastructure is on fire, not only you should have one dashboard in one set of metrics that developers, ops, and security people all look and collaborate on, but this should work for all of your orchestrators, and it should work in a role-based access control fashion, such that you can tell your system who the fire marshal is and who the driver is, who has control, the ability of responding to fires. So role-based access control plus visibility across all of your orchestrators and all of your applications allows you to have this within your infrastructure. And the final one that I want to talk about of the post-crash capabilities that the Indy 500 cars have is a data recorder. It turns out, and this is really cool, when a crash happens in Indy 500 and the doctors and the paramedics and everybody's rushing to the driver to help them out of the seat, they already know what happened in the crash. They know the G-forces that the neck was subject to. They know how the car is deformed. They have the data to be able to actually take care of the patient, of the driver. And all of this data is being collected in real time. So when they get to the driver, they know what to do. This is really important for us to have also in our systems. And this is really where the Docker security ecosystem shines. It is not just about data collection. In this case, I have an example of a security system that is out there. In this case is a system called SecRox. There's companies like Twistlock and Aquasec, Encapsulate, and Sysdig Secure that allow you to have equivalent systems and collect this data in one place. And it's not just about collecting metrics that will help you with the response in the case of an attack. It's really about showing them in a way that you get to understand what is happening. And so in a usable way, you get access to this data, get access to this metric, such that when you are responding to the incident, you know what happened. So as we've seen in both the hospital and the Indy 500 case, collecting a ton of data about what's happening, it's actually useful, and it leads to better patient healthcare. But access to this data should be safe, not just secure. And in order to design these safe systems, you really need to take out the barriers that stand between you and the final real-world impact of these data breaches. Because doing this ensures that you will have the same methodology and the same devotion about protecting your data as the engineers that designed these cars had about protecting their drivers. And so I want you to remember that with careful engineering, you can both go fast and be safe. So I ask of you, go out there and save lives. Thank you very much.
If you have any questions, just raise your hand or come up to the mics if they're next to you.
Questions about Formula One? I don't actually know anything about cars. There's a question over there.
Yeah, my question is about so you said talked about putting the Docker image in a state of freeze. Do you have more information on mechanism to do that?
Yes.
In Docker?
So Containerd already implements this. It allows you to freeze memory and actually push it to a Docker registry, such that you can then pull it and rerun a Containerd container using that frozen memory. And with Docker, you already have the ability of freezing the layered file system because you get to commit. So a Docker commit effectively gives you a tar that is the description of everything that changed from the moment the image ran. So you already have the two components you need. You have the ability of freezing memory with Containerd, pushing it to a registry, and you have the ability of freezing your file system using Docker commit and pushing it to a registry. No more questions? Perfect. Oh, there's a question over there.
You mentioned key rotation. Can you explain how that works? Does that include certificates as well, or is it just the sort of the private keys that you're rotating? And can you sort of instrument that from within the Docker Enterprise console?
Absolutely. So key rotation, I mentioned that in two different settings. I mentioned in the Docker Content Trust setting, in which it is the mechanism by which you sign your images, and that allows you to have an offline key that should only be brought online when you want to do rotation. So it has a tiered key system that allows you to effectively have this transparent key rotation guarantee. So I talked in that context of image signing. I also talk about it in the context of the actual orchestrator itself. So I talked about it on Swarm implements this by default, and out of the box you have mutual TLS. Every node that joins gets its own certificate, automatically rotates that certificate, but the main problem becomes if the manager gets compromised and the certificate authority gets compromised, what do you do? And so to my knowledge, there are very few systems out there and not really any other orchestrators that allow you to effectively go and resist a CA compromise and effectively resist the compromise and have a transparent key rotation mechanism that allows you to have the manager be completely compromised and you still rotate the root of trust out throughout all the nodes. So that, what effectively is happening is rotating the certificates of every node to no longer trust the new root CA, but to swap completely the trust to the CA that you generate when you rotate it.
Manually set that by policy?
So the question is, can you manually set up as a policy? Right now, no, but you can call the API to force a rotation. And for us, it is can be either an interactive process or not. So you can say, please rotate, and when all the steps are done, you kind of like ensure that all the nodes have rotated, or you can do the really cool demo of having 10 nodes or 100 nodes, click a button, and there's a progress bar that shows you every single node removing the trust from the old CA. That's actually a really killer demo. Didn't have time for it, unfortunately.
Hi, thanks for the wonderful session. How much of this content and recommendation is covered by the experimental Docker trust command?
In terms of the whole talk or specifically the rotation?
No, whole talk, please.
So the whole talk, so this was done not to be effectively a plug to our own things, but for the by and large, our systems in Docker Enterprise Edition covers the large majority of the things that I talked about. So that's kind of obviously the goal. There's some things that it doesn't cover yet, but this is kind of like the guiding principles that we're aiming to achieve. And this is where the talk came from, is more the guiding principle than what is there. But a lot of these things are there. The rotation is there, the signing is there, the pipeline trust is there, the obviously minimal trust, and the ability of rotating all these keys is there. Things like container freeze and the ability of porting these things to another network are in the underlying substrate, but have not been shown into an actual higher level API. So effectively they will be coming, and things like crypto anchors are a little bit data dependent, but they might actually make their way eventually to the Docker infrastructure in general. So it's really about a hybrid of where we want to go and where we're at right now. Perfect. Thank you so much.